Time for more fun with matrices. These matrix creatures come in all rectangle shapes and sizes. Remember that matrix multiplication is associative but not commutative. This means that if you need to multiply a chain of matrices together, you cannot change the order, but you can add parentheses. Let's say you want to multiply these matrices together. Where we put the parentheses will change the number of computations we must perform. Since the goal is to do as little work as possible, we have a method of calculating all the possible cost and put the parentheses where the total cost will be the smallest. We use their shapes to make a list of all the different dimensions in the set. We will make up three variables. J is the beginning index of the section we're looking at, and I is the end index. K is the matrix to the left of the split. So if we're looking at matrix 2 to 5 and looking at a break between 2 and 3, these will be the values of J, K, and I. Next, we make two diagonal charts. One, called M, has the same number of rows and columns as the number of matrices labeled with the possibilities of J and I. The other, called S, has the same setup minus the bottom row. The bottom row of the M chart is just looking at one matrix, so they take 0 computational cost. The symbols are unnecessary, but help me see what's going on and talk about it. We will also go ahead and put the dimensions on there for convenience. On the S matrix, the best placement for K is already known for the bottom row, since there is only one way to parenthesize two matrices. The alien represents the cost of multiplying the first and second matrices. If we want to find the value of the alien, we multiply the three dimensions involved in making it. The acorn does the same, but is the cost of multiplying the second by the third. The same method is used for calculating the button and apple. Once we get to the third row, we have three options. We're considering all the ways to multiply the first three matrices together. We could choose the 0 all the way down to the left plus the acorn, or we could choose the alien plus the 0 to Adam's right. We then compare this to the other option. The option using the alien has a lower cost, so we will take that one, and this means the best placement for K is 2. We continue this pattern for the beaver and cubes. Once we get to the fourth row, we have three options to compare. For this middle option, we have two non-zero components we must add. After calculating all the options, we can see that the first option is best and fill in that cost, and this split will happen at K equals 1. This dynamic program is using tabulation. The butterfly encompasses the entire chain. To figure out the best places to put parentheses, we look at the top box on the S matrix. This 4 tells us that for the outermost parentheses, K equals 4. Next, we see that this butterfly was made using the berries and the 0 on the right. The 0 on the right just means the last element is by itself, so we don't need to investigate it further. For the berries, we find the corresponding place on the S matrix and break up the chain further in that location. Then we trace the berries back. The beaver is made of the 0 to its left and the button is made of 2 zeros. So we've traced all the paths down to the 0 row, which means that all of the matrices are by themselves. Now we have the final result of where the parentheses go. This is technically right. However, if we want, we can take off some of the redundant ones for the sake of simplicity. This will be the most cost-effective way of arranging them. It may seem like a lot of extra work, but can actually make the overall code run faster. Thank you so much for going on this adventure with me. Please like and subscribe to Kristyns Kunique.